This is not so easy to so it's just many times multiplying the two and then you finally get there. So if one wants to solve it without the logarithm button, let's try like this. It's already 4. Yeah, well, that wasn't anything. Mm-hmm. Yeah, now we're close. So that was 10 times. This from the book, it's a bit. So there's always a different base. When would you have that kind of a base? But I have a logarithm bottom here actually that I can put any base I want. So I could put there this 0.1. And then I would get something, even if I wasn't supposed to use that. And then there was the 0.01. So again, I could think it in the way the base power of something, and it becomes this. Then I can even take it with my thingy, with my calculator, if I didn't remember the 0.1 times 0.1 is 100 and 0.01. So that seems to be 2 times. Which is 0.1 times 0.1. Is this 0.01? And why would that be 1/10? So it would be 1/10 cents. And then it's pretty clear because then it's like 1 times 1, 10 times 10, which would be 100. And that's, of course, the 100, right? Oops, too many zeros. There. 313. But now we know already something. So it means ln here is actually the e. So it's not like x. So it's like, well, e in the power of x is e in the power of 313. You can try it like that. So obviously the x should be the 313. Because the ln was the log e. Again, I don't remember what ln meant. The log the base. So then you can already see that, okay, this must be the 313. Again, the same. So it's the minus. I don't write it again because the e is the base. And then LG. So that it's LG is the 10 based. So this is obviously now 3. Maybe I can put it there. Well, this is again the same thing as the ln thing. 15, so is x, so I know that it's the 10 base logarithm. 10 in the power of 15 must be 15. This is the 10 base logarithm. 1 is x. Notice it's a bit slow. Which would need 10 in the power of x is 0.001. And this 0.001 seems to be like, it's like 1 divided by 1,000. So obviously there has to be some minus thingy here. To get this big. -3, yeah. So 10 base logarithm, or you go to get this, you have to have the minus, or now the G seems to be, I'll just write the G here. There was the HG minus 23, and I already know that it's that. Do you think this is easy now, or you have to think a bit?
Yeah, maybe it's back to the
Because it's a bit, yeah. Well, like to teams F4. So next thing was the rules. Single logarithm. Hmm.
What's the? So I was Googling and it said the log button is to the base 10. LM is to the base
E, yes.
with some mathematical constant.
Yes, it's the, well, I didn't say, but what is it called? It's some Neper number, how to say it in English.
But
I
then,
think somewhere here, maybe, does it say about the Neper number?
but then I don't.
But this says that it's the LG, but in yours calculators, it's the
Yeah.
just marked as log.
Well, why do we? Oh my God.
But we need two base numbers. Yeah, it is the E's, I think, you for the X both modeling, and the base 10 is then for the acidity and the sound intensity,
Right.
and the Moody diagram
Yeah.
and the Richter scale.
Yeah.
So there's two, because people have, there's many things about this E, the Neper number, that makes it mathematically interesting number.
Yeah.
And a lot of history for sure. There could, it would be nice, even if in math we would do some presentations and somebody would tell about them sort of interesting mathematical a bit in just in theory.
Yeah.
It's not what we really do, but it's many ways nice. For sure, you can find some nice lecture from the Khan Academy, for example, where they explain the specialties of it.
Yeah. It's just, I don't, it feels like there's so many just random sounding numbers to me. You know, like
Yeah. But it's not, because some people were doing the hundreds of years of the research,
Yeah.
and then they realized that
This is important.
this is, or you can model something with this.
Yeah.
So this is how it behaves, and
Yeah.
this is what you always get as a constant
Yeah.
from there. And then they figured out this number. For example, the E. This is like for sure, like some clever people were doing a lot of work, so now we can use it. But then once for the exponential growth, for example, it's just because they, like somebody has done research and done measurements and realized that it follows this kind of a curve.
Yeah.
And the curve you get with this kind of a mathematical function. So you actually, this is the, the law of the nature, and there is this number.
The exponential.
Yeah.
And then tangents are, why are they not? They're also the same shape. No?
The what?
Tangent. You know how you have the sine is like that.
Yeah, the sine curve and the cosine
But
curve
I think,
and the tangent. Yeah, that's curve. And then you have for example, what is it? Polynomials, where you all get, but there you always have the exponent.
okay.
Like x in the power of something. For example, x in the power of 2 is the certain type. Then you have it in the power of 3, and then it starts to go a bit like curved.
Yeah.
More curved. Yeah.
Mm.
And then you realize that you can use it to model the behavior of something.
Yeah. Seems so crazy, like.
Yeah. And then this is why we do this now in this basic level, because then you use these applications where these functions are used to model the behavior of your something that that you study.
Yeah.
Yeah.
Just plug it in and then.
Yeah.
What should the answers to be? Yeah. What was the answer to 1B?
1B,
Yes.
3. 1, what?
Yeah, yeah. Okay.
I can put the solutions there because there are the solutions anyway. No, this is not. Where have I been? Those ones. There are some old solutions that have been done on the Finnish course in Finnish. Oh, it was 11. 10. Oh, let's put the brackets or hey. Use again many, what do you call them? Formulas. So there would be yeah, this could be done the other way. So then we do know what that is. Okay, then there's even some. Okay. A-based log of everything multiplied. Then I can just, oh, was it 3 volts? No, that was 2. No, that's 2. That's okay. So I'm gonna calculate the exponents together. Oops, log. X in the power of R in the power of 7. Okay. And then I could do many things, maybe to this as well. If I wanted to still continue this, why not? How would it look like? No, it doesn't fit. But then I would have log X in the power of 5. It's log near the, I needed the R. X in the power. Yeah, now it was the Y. 7. And then I could still do something to it. And then that's all I can do. 5 log R. Or was I supposed to express it as a single logarithm? This is something that I'm not supposed to do anymore. I just did it. It doesn't look any nicer. It's just rolled. Don't do maybe this. Okay. So this is just using these rules that are there. These are the first ones. These obviously we didn't use. Then it's still some nasty looking thing. Well, there's a solution for that somewhere. Maybe I can already go to the next equations because there's not much time. So I would solve some like this. I can take I will take the 10 base LG. Well, I'll just write it as a 10 based logarithm. Log 10 like that. I think it's written. Okay, and then I go there log 10 of the 10 is log d3 and I know this means this, yeah. I can just then, or it's an x is this, which I can of course then I can check what it actually is. So 1, 2, 3. Something like this. 2.09 about. And then if I want anybody to look as a graph, so here I would somewhere have 1 where it always goes from. And then here somewhere I would have the 1, 2, 3. Okay. Well, 1 and 2. About 2, it was already there. About a bit more than 2, 2.1. And it went from here because the curve always goes there. Wow, that was quite steep. And why is it always go from there is because if the x is 0, like it's there, x is 0 there, of course, then if you put you want to take the then based logarithm, and it's 1, 1. You have to obviously raise this x now. Then you get the 10 in the power of x is 1. And how do you get 1 out of it? Then you have to put there the 0. And this is always whatever base you have in the power of 0, any base e in the power of 0 is also 1. Maybe it's somewhere here. Yeah, it's there. It's any base you have to 1, it always goes through 1 at the x is 0. So you have it there. Page 8, and it looks like log to get 1. The exponent needs to be 0. So this is how you always get at least 1 point for your always goes when x is 0, the y is always 1. So it always, and then it goes.
So y is always 0. No. Okay, 0.
Because everything in the power of 0 is 1.
And then you would just do like log 10 to the 1 and get each point. So like on this curve,
Mhm.
how would you get this curve?
Well, it was just a sketch.
Yeah,
It's not very accurate, as you see. Here's 1
yeah,
and here's 1, 2, 3. It's just like a sketch a bit. So I knew 1 point and then another point. About 2.1, I get the 100, and
yeah.
when there's about 2.1, the y is 133. It's just a sketch to
Yeah.
realize sort of what this whole thing here meant. Mhm. So then if I would have here the e, of course, I would take the ln, because the ln was the base was e. So then I get log e. I can just write it like this as well, so I can see clearly that, or that was log ln. I'll write it again. So there would be ln e ln 13. So now to see clearly, it means that I have an e-based logarithm of this. So I know, of course, that it's the x here is ln 13. And then I just take, what is ln 13? Something like this. So it's about some 2.56, 2.6. And I again can sketch, or even if I didn't want to, I can still do it. And then I would have here that somewhere the 13. This is not really in scale again. Here somewhere I would have the 1. And then I know that when I'm at about 1, 2, 2.5, a bit more here, I would have my 2.56. I would be at the 13. And again, the same looking curve here. Wow.
Like the logs just use my brains. I don't know why.
Yeah, well, it's just something that your brain didn't do
Yeah.
that much. So then you have to be like adjusted, like.
Like, but even this B, it seems so simple,
Mhm.
and then it feels like I'm having to work so hard to like, yeah, each step.
Yeah, because it's not like you just did it just like the
Yeah.
other day.
Yeah.
Yeah.
You just switch it up.
Now you can take a 2 base logarithm, or because I can take a 2 base logarithm, but not everybody has the button, that nice button. So you can take any logarithm. Just take for the 10 base one or the ln. Doesn't matter. So then I don't get everything so nicely like I would with the 2 base logarithm, but it doesn't matter. Is ln 50. And then I would use the rule here, which was the log that I can drop the exponent. Log this one from the technical formulas. And then I drop the exponent. ln 2 and then I would just ln, and well, I can already divide with 2 ln 2 because I have to get rid of the 2 as well, obviously. Yes, 2 ln 2. So then I have only the x there, the ln 50, and under here I have the 2 ln 2. And then this looks nasty, and I can modify it. I don't have to. I can just stick it to the calculator and the ln's there. 2 ln 2. I don't think I have to put the multiplication mark there. And that's something. Again, some are the answer. 8 to something, 2.8.
How long will we spend on these? Like, it's not like next week. We just never do this.
Next week. But we are, this course for you is to get you ready for your courses to come.
Yeah.
So I would expect that you do these things then in the applications, engineering applications on the further courses. That's why we go through them here.
Yeah.
But I don't know how soon.
No,
Yeah, that's the thing. I don't know if when
Yeah.
that's gonna happen. So now we have do you know the basic rules? And then
I get it.
again you'll be okay.
I'll be doing math until summer.
Yeah. Maybe you can do something else as well. So 1, 2, 3, 50. I'm almost at 3. And at 1, I'm here. And again, I can draw a curve. And it looks exactly the same. There's just 50 now here. And then you can draw this a lot nicer with, for example, the GeoGebra, if you want to. Hopefully it would be really good applications would come, but I don't know when that's gonna actually happen. But there's a lot more equations to solve. You can do them at home. I think the solutions are there already, and we can still continue next week. And for the next week, we still have the ones with some written exercises, you know, like where you have to make yourself the equation and then solve it.
Okay.
Which was some sound, pH, and exponential growth.
Yeah.
Yes. Thanks.
This is interesting, isn't it?
Yeah. But,